Okay. So it's saying f of x equals -3 when x is not equal to 2, and f of x equals 0 when x is exactly 2. So if we graph this based on the piecewise functions we did last week. All right? X not equal to 3 is 2. We got a dot there. We're going that way. We're going that way. And then the only moment it's at 0 is x equals 3, so that's a closed dot. All right, ladies and gentlemen, that is not your answer. That is. So the answer is 2. All right? Remember, it's not the actual value when you have piecewise functions. All right? All right? So you can do it without graphing if you simply realize find the limit of f of x as x approaches 2, where f of x equals either -3 when x is not equal to 2, or 0 when x equals 2. You got a 50-50 shot. Either -3 or 0. Which one is it just by looking at it? Good job. And that's it. All right? So now please work on those two. Find the limit as x approaches 1. Find the limit as x approaches 2, please. I'm not going to find out. Relationships work two ways. They can move towards you as well. Relationships work two ways. People can move towards you as well. If you make it a one-way street, you're going to get hurt. You're just going to give. You're going to get everything back. Did I get everybody with the homework? Yeah, Lally, homework. It's school. You may not believe that he just came back to a little vacay on the way out the door. You're junior year, but it's actually school going on. Thanks for welcome back to society. Did I get you? Okay. Yeah, I got you. I got you. Talk. Okay. All right. All right, now with this one, even though it's piecewise, if you plug in 1, what's 3 times 1? 3. 3 minus 1, 2. When you plug in 1, you also get 2. So from both directions, what is it approaching? 2. So the answer is 2. If you graphed it, all right, if you did graph it, thanks to be you. All right, and then if I do 0 here, -1, it would look something like that. It would just change direction, but there is no open dot. That makes sense? So if they approach the same value from different directions, there's no open dot. All right, now, when I do the second one, when I plug in 2, -4 minus 3 is -7. 6 minus 5 is -1. So now they're coming from different values. So now it matters. That makes sense? +1? Yeah, sure. We'll go with that. Are they still coming from different values? Yes. So there's 2, which is the value that we're talking about as it approaches. All right. One of them is -7. And that's an open dot because there's no line underneath. And then 6 minus 5 is 1. That's a closed dot. Ladies and gentlemen, that one does not exist. Whenever you have, and we're going to talk about it in a second, whenever it goes to a different number from both sides, it does not exist.
So you just like plugged in the 2 and you got 2 different numbers right away?
Most likely say it does not exist. We're going to talk about it in a second, yeah. Unless it's something like this where it's just a single point. When the first one we did, when it's just a single point, now it does exist because you're only talking about the 1 point. But the idea is, and again, if they're coming to the same point, you are right. So yeah, if they go to the same value, pretty much you're good to go. Make sense?
Yeah.
All right. Limits that fail to exist. So building on that, as f of x approaches a different number from the right side of C than it approaches from the left side, f of x increases or decreases without bound as x approaches C. F of x oscillates between 2 fixed values as x approaches C. All right? So for example, for the number 1, the limit as x approaches 0, absolute value of x over x. Right? So that's the graph of that function. From the negative, it's going to -1. From the positive, it's going to +1. All right? So it's a function, it just doesn't have a limit at that value. Does it have limits at other values? Yes. It's just the limit they're asking about, it doesn't, because that's 0 to different values. So that's what we mean by it goes to a different number. All right? Everybody good? All right. Without bound, it goes to positive and negative infinity. Think rational functions, odd polynomials, tangent, cotangent, secant, and cosecant. Those are all the ones that have asymptotes. So if you have it approaching an asymptote and it's going in different directions, like one's going, now if they're going the same direction, you're fine. All right? But the idea is if they're going in different directions, then they're not fine. So for example, if we graphed 1 over x minus 3, all right, and we were approaching 3. As it approaches 3 from the left, where are we going? Up. But we're going down. So therefore, there is no limit. All right? Everybody good? And then the last type, oscillates, varies between 2 values so frequently that you cannot determine a limit. Think trig functions in the form 1 over x. So if I do the sine of 1 over x, do you have any idea as it approaches 0 what it's actually getting to? No, because it continually increases, gets closer together. So therefore, when you have something like that, the limit does not exist. Good? All right, on the back. Examples. Examples. And if you want to sketch these for your own use, that's your choice. So we're looking at the limit as x equals 1 of 2, absolute value of x minus 1, divided by the expression x minus 1. Once again, all right, get the habit with absolute value. In other words, the two functions are exactly the same, except one has what symbols around it. Absolute value, when that occurs, it's not going to exist. Unbounded, 1 over x squared. All right, even if they're going in the same direction, there is no limit. All right, so they don't have to be going in different directions because they're both going to go to infinity. Therefore, that does not exist. Okay? And then oscillating, we just did the limited sine of 1 over x. So we'll do the cosine of 1 over x minus 1. All right. And you can see it oscillates as well. So I'll leave that up there in case anybody wants to sketch those down. And then we will talk about the easiest ones, which we left to the end to send you off a good note. And that is direct substitution method. Good. All right, direct substitution method. Sometimes the limit x approaches c as f of x equals f of c. In such cases, we evaluate the limit by direct substitution. These are considered the well-behaved functions, functions with non-zero denominators. So, all right, limit x approaches -3, 2x squared plus 4x plus 1. If I sketch the graph, you don't necessarily have to do this. All right? The vertex would be at -1. -2 minus 4 is -1. -1. Then you got a parabola looking like that. Are there going to be any issues with a zero denominator or any breaks at all on that function? No. So all you do is plug in the value into your function. If I plug in -3 squared, I got 9, 18. 18 minus 12 is 6. 6 plus 1 is 7. Boom, I got 7. Yes, ma'am. The vertex? -b over 2a is your vertex from when we did the quadratics. That brief little stint. B is the number in front of x. A is the number in front of x squared. Okay, now, normally quadratics, we talked about earlier in the year, go over 1, up 1, over 1, up 3, unless there's a coefficient, which is 2. So instead of going over 1 and up 1, you go over 1 and up 2. So that's where the next one came from. And you just have to sketch it out real quick. Right? There's none. It's just to show you that there's no, the idea is you don't have to, but the idea is that shows you why. That justifies it. So if they tell you to graph, they give you specific directions to graph, boom. If you, and again, we're going to talk about this in a second. If you can do it just by plugging in, then you do it just by plugging in. And these are the ones you can always do that because there's going to be no chance of you having an issue. All right? Limit e to the x as x approaches 3. E to the x looks like this. All right? All right? You can either use plugging in like we just talked about, or you can just trace it until you get to 3, which of course I need to go bigger. And 3 is at about 20.086. Oops.
Find it. Plug in 3 for what?
You just plug in 3 for x. It's an exponential. Notice they're both exponentials. You're never going to have a problem with it. You got a calculator and you hit second natural log. That's where he is. All right. Good. Now you do have to be careful, ladies and gentlemen, with the inverse of e, which is the natural log of x. Because remember, you can't go to 0. Because it's what? Undefined. So with exponentials, you're fine. With logs and natural logarithms, you're going to have an issue. Because you can't have 0 and less. They got to be positive. All right? And then the last one, ladies and gents, is 6 over x plus 4. All right? 6 over x plus 4. And we want to know the limit as it approaches -5. All right? -5, -6. With rational functions, the only time you worry is when the limit is the what? Rhymes with asymptote. Asymptote. Is -5 the asymptote in that function? Nope, so you don't have to worry about it. Is -4 a problem? Yes, -4 is a problem. All right. So if it was -4, then it wouldn't exist. Make sense? Yes. If it's a whole, you're okay. Those are the ones we went over on Friday. If it's a whole, you're okay. With these, you're not, because it's an asymptote. Because it goes without bound. That's what we talked about in the beginning of class. So if you have to, and you have to in the homework, explain why it was -4, you could either say it's going in 2 different directions or it increases without bound. I would accept either one. All right? That one is whatever you get when you plug in -5.
Oh, okay.
So that's another one you just got to plug in. All right? So it comes out to be -6 when you plug it in. All right? Okay, let's take a few minutes to talk about the next homework. So tonight you have the first set, which is page 758, 757, 910, all these. Everybody's good with that? Everybody understands the tables you put in? All right, so these are going to be one, so you're just plugging in those values. After that, you can use anything you want. You can use a table, you can sketch the graph, or algebraically. Everybody good? Okay, now, okay. The homework for tomorrow night, that covers what we did today, page 758, 27, 29, 30, blah, 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 and all those numbers. The directions for each section are on top if you don't want to look up your book. So 27, 29 through 30, you graph it and find the limit as x approaches 2 if it exists. So for 27, 29, and 30, you got a graph. For 35, 37, and 41, they give you the graph. They give you the graph. It says use the graph to find the limit if it exists. If the limit does not exist, explain why. The one thing you do need to add, ladies and gentlemen, just so you know, I knew I forgot to do something before I made the copies, is this is an open dot and that is an open dot. Because if I plug in -2 to either one, what's -2 plus 2? 0. Can I have 0 in the denominator? No. All right, and then 37 and 41 are other examples. If you can't do it, you just explain why. So those are more explaining. All right. For the next batch, 43 to 46, use a graphing utility to graph the function and then use the graph to determine whether the limit exists. If the limit does not exist, explain why. Now, Miss English asked, what's the point of graphing? You don't physically have to graph it, all right? But you may want to use the graphing calculator Desmos to do so. And then you can just trace your graph. The problem here, when I plug in 0, what's 1 over 0? It does not exist. So you have to look. Now, is it possible the limit doesn't exist at all? Yeah. That's when you go back to the oscillating and all that stuff. So that's the graphing. You don't physically have to graph it, but you have to use the graph to find it. All right? Same thing with 44, 45, and 46. And then 55 through 70, it says to find the limit by what? Direct substitution. So all you're doing is what? Plugging in. There shouldn't be any reason to do anything else. All right? Everybody good? All right, you got about 18 minutes to get started on that. Those of you at home, if you would like to depart, have yourself a lovely day. We'll see you back here tomorrow.
What's the first homework? Yeah, I need that too.
Nice. Or the new one. Notes. Yeah. If you need tonight's homework, it's up here, and if you need the notes from product interaction, those are up here too.
Nick, how's the notes do?